To see the world, your eye relies on a flexible protein called crystalline. To focus at different distances, tiny muscles actively squeeze and stretch this soft lens, bending light until it hits your retina. Trilobites worked with a different set of rules. Instead of soft, pliable proteins, they grew their compound eyes out of solid rock crystals. Their lenses were made of crystalline calcite, the exact same calcium carbonate mineral that armored their heavy exoskeletons. Building a precise optical instrument out of rigid armor plating creates a mechanical paradox. Unlike modern biology, which adapts through movement, these lenses were fixed in stone. Seeing through solid calcite presents two major obstacles in optical physics. The first is birefringence. Calcite naturally splits incoming light into two separate rays traveling at different speeds. For a trilobite, this results in a double image. Every object in view appears as a blurry, overlapping ghost of itself. The second problem is the lack of accommodation. Because these lenses are rigid rock, they cannot squeeze or flex to focus on objects at varying distances. Without the ability to change shape, a standard spherical lens creates severe aberration. Light from the edges and the center would focus at different points, leaving the world in a state of permanent blur. By the laws of optics, these creatures should have been effectively blind, stuck in a world of doubled, out-of-focus shapes. Yet they dominated the seafloor for millions of years. To solve the double vision problem, trilobites didn't change the material. Instead, they manipulated its microscopic orientation. Calcite crystals have a single optical pathway called the C-axis. Light traveling along this line passes through without splitting. Trilobites grew their lenses so this axis was perfectly perpendicular to the eye. By aligning crystals to incoming light, they secured a single sharp image. By coordinating the growth of millions of microscopic rock crystals, trilobites bypassed the native physics of their own armor. Fixing the focus was a more complex engineering challenge. Within the suborder Phacopoena, trilobites developed a structural layout called the schizochroal eye. They solved spherical aberration using a doublet lens, an optical unit of two distinct layers. The upper layer was pure calcite. The lower was a different material, like chitin. The interface between them corrected the focus, converging light rays onto a single point. This dual-layer system provided a massive depth of field. It kept objects both near and far in focus at the same time, without the need for a single moving part. This specific, mathematically ideal lens shape was only described by human physicists René Descartes and Christian Huygens in the 17th century. Trilobites had already implemented this exact geometric solution 300 million years before the invention of the telescope. These optical adaptations were closely linked to the environment of the Cambrian seafloor. Compound eyes are highly sensitive to motion, making them effective tools for monitoring the water column. If an active predator like Anomalocaris swam overhead, its shadow would trigger an immediate response across the trilobites' thousands of lenses. This early warning system gave them the seconds they needed to burrow or flee, keeping them a step ahead of the ocean's first major predators. By using minerals as sensors, trilobites turned their protective shells into a sophisticated surveillance system that defined the early arms race of the Cambrian explosion. But the history of these eyes ends with a strange reversal. As some lineages moved into muddy seafloors or the deep ocean, they began to lose their sight. This is known as secondary eyelessness. Over millions of years, these deep-sea dwellers gradually reduced and eventually abandoned their crystal eyes. In the pitch-black benthic depths, the biological cost of growing perfectly oriented calcite doublets offered no return on investment. It reveals a core principle of evolution. Biology can utilize complex physics to solve a problem in stone, but it will discard that solution the moment the energy cost outweighs the survival benefit.